Section 5.5 is going to be integration by substitution. Before we get into exactly what integration by substitution is, what I'd like to do is just a little exploration of the chain rule. So if you'll recall, the chain rule says if you take the derivative of a composition of functions, I will pick for my outside function capital F and for my inside function little g of x. Then I can write that using the chain rule as capital F prime, where g of x is plugged in, times g prime of x. The notation that we used earlier in this chapter was capital F was an antiderivative of little f. So what we're going to do now is we're going to say let little f of x equal capital F prime. So we're consistent with that notation. So I can write this as f of g of x times g prime of x. Another thing that we saw earlier in this chapter was that every time we had a derivative rule, we could create a corresponding integration rule by integrating both sides. So I'm going to go ahead and take the integral of both sides. On the left, the integral of a derivative, because those are inverse operations, they'll just wipe each other out. So integrating both sides, on the right-hand side, we'll have the integral of f of g of x times g prime of x dx. And on the other side, the integral of the derivative will just leave me with the original function, capital F of g of x, of course, plus a constant c. So now let's do a little bit of relabeling. I'm going to let u equal g of x. And using this identity, u equals g of x, if I differentiate both sides, on the left I'll have du dx, and on the right I'll have g prime of x. And then using our knowledge of differentials, I know that the du and the dx can be split up. So I'm going to multiply both sides by dx. So du is g prime of x dx. So what I can do here is I can say that this g prime of x dx is just du. This g of x I can write as a u. And this g of x I'm also going to write as a u. So then this equation is going to look like the integral of f of u du equals capital F of u plus c. This is really what integration by substitution is, and this is the process that we're going to do. When I have a composition of functions, we relabel the inside function as u. We have to take care of the differential, relabel it as a du, but then we're just going to be integrating a function, and we get its antiderivative. So this is substitution. All right, let's look at an example. Suppose I want to integrate the quantity x to the 5th plus 2 raised to the 6th power times 5x to the 4th dx. As we go through this example, I want to make note of what steps we use to solve this. Our first step is going to be to identify what is the inside function and call it u. So we're going to pick a u looking for an inside function. In this example, I think that x to the 5th plus 2 is an easy choice. So we say let u equal x to the 5th plus 2. As soon as we do that, just like we did earlier, before I even replace anything with a u, I look at what the derivative is, differentiate both sides. So when we differentiate, the derivative of u with respect to x is du dx. When we differentiate on the right, we'll get 5x to the 4th. Solving for du, I multiply both sides by dx, and I get du is 5x to the 4th dx. So that 5x to the 4th that we started with times dx all together becomes our du. This is different than the substitution that we've done in most of math before this. Usually in math we take one simple thing and we replace it with a complex thing. Here we're taking a complex expression and replacing it with a simpler one. So we're going to substitute for du and also for u. I'm going to really emphasize substituting for du. You should make a habit out of doing that first. If you forget to substitute for the du, you're going to end up with something meaningless, and you'll end up likely getting stuck or getting the problem wrong. So this 5x to the 4th dx becomes du. X to the 5th plus 2 becomes a u, and it's still raised to the 6th power. So we have an integral of u to the 6th du. And I can integrate that like normal, because u is my variable. We just use the power rule. Add 1 to the power, divide by the new power. Don't forget the plus c. And so the last step is just to integrate. So we integrate with the variable u. I misspoke. It's not really our last step. One more step after that. We started off with a function of x's. We should end with a function of x's. So now we substitute back. So I say, okay, u is equal to x to the 5th plus 2. So I replace the u with an x to the 5th plus 2. Let's look at another example. So here we're integrating a trig function, the integral of sine of x minus 5 dx. Once again, we want to find an inside function to be our u. So we're going to let u equal x minus 5. Then if I differentiate both sides, du dx is just 1. So du is equal to dx. That's an easy substitution. So this dx is going to become a du. This x to the this x minus 5 is going to become a u. It's inside the sine function still. So we're going to have the integral of sine of u du. Because our variable is now u, and we're integrating du, we can integrate like normal. Integrating sine of u will give me the opposite of cosine of u plus c. And then our last step after we've integrated is to substitute back. We have negative cosine x minus 5 plus c. Let's look at another example. Here we're integrating the fraction 1 over 1/3 x minus 8 all raised to the 5th dx. This is interesting because we note that in the past we said we don't have a quotient or product rule for integrals. This looks like a quotient, so that might be a problem. Sometimes U-substitution simplifies things enough that we get rid of the quotient or the product. So let's see what happens here. I'm going to try a U-substitution. So we're going to let u equal the inside function. Since I have stuff to the 5th, I'm going to let u equal what's inside there. So we have 1/3 x minus 8. Now I differentiate, so du dx is just 1/3. So if I solve for du, I get du is 1/3 dx. But I don't have a 1/3 times my dx. The 1/3 isn't, there's no 1/3 around. But that's okay. Constants don't mess things up. What we can do, if the constant doesn't match, just move it back over by the du. Multiply both sides by 3. So 3 du equals dx. So now we can replace the dx with a 3 du. In the denominator, we have stuff to the 5th. That stuff is going to become a u. So we're going to have a u to the 5th. I'm going to take a step to rewrite this before I integrate. The 3 I can factor out of the integral. And 1 over u to the 5th I can write as u to the negative 5th. So now I have a u to the negative 5th du that I'm integrating. And we can integrate using the power rule. Add 1 to the power, divide by the new power. And now that we've integrated, we can substitute back. I'm going to rewrite 3 times u to the negative 4th over negative 4 as a negative 3/4 times this. And I'm going to replace the u with a 1/3 x minus 8, all raised to the negative 4th. And that looks good enough. Our next example is the integral of x squared times the square root of x minus 1 dx. And this one is a little bit more challenging. It's clearly a product of two functions. And I'm not really sure how we're going to integrate a product. But again, I don't have to worry about that because I have an inside function, x minus 1, inside the square root function. That's a more pressing problem. So we're going to start with a U-substitution and see what happens from there. So I'm going to let u equal x minus 1 because it's inside the square root function. Then du over dx is 1. So du is just equal to dx. So the dx I can rewrite as a du. The inside of the square root I can replace with a u. Instead of writing it as square root of u, I'll write it as u to the half power. And I say, well, wait, what's going on with this x squared? I can't replace an x with anything because I don't know what x is equal to. So now I have a mix of x's and u's, and that is absolutely no good. We absolutely do not want to integrate two variable functions. That is a complicated process that you don't know how to do, and that may not make sense here. What we need to do when we substitute, if we're going to get rid of x's and make them u's, we have to get rid of all of the x's. And if they don't all go nicely, then we have to do a little work to make them go. So what I'm going to do is I'm going to say u is equal to x minus 1. What is x equal to? I'm going to take that equation and solve for x. So if I add 1 to both sides, u plus 1 is equal to x. So I can replace the x with a u plus 1. So now let's look at where we're at. We had a composition of functions. I had a function inside a square root. And we don't have that anymore. But I have a function inside a squared function instead, and I still have a product rule. So it doesn't feel like I've made a lot of forward progress. However, I can't break up square roots at all. They don't distribute over addition or subtraction. There's really no way to get rid of it. Squareds, I can FOIL things out. So this is still going to be something a little bit more manageable than what we started with. So I'm not ready to integrate yet, but I can do more algebra stuff. I'm going to FOIL out the u plus 1 squared. And we get u squared plus 2u plus 1. Now what I can do is distribute the u to the half to each of my three terms. So u squared times u to the half, when I multiply like bases, I add the exponents. 2 plus a half is 5 halves. 1 plus a half is 3 halves. And u to the half times 1 is just u to the half. Now we're ready to integrate. So the u to the 5 halves, when I use the power rule, I add 1 to the power, divide by the new power, but instead of writing divide by 7 halves, I like to write multiply by 2 sevenths. For the next term, when I add 1 to the power, we'll have 5 halves, divide by the new power, or multiply by its reciprocal. For the u to the half, when I add 1 to the power, I get 3 halves. Dividing by 3 halves is the same as multiplying by 2/3. Of course, don't forget the plus c. Now we can go back. Remember that u is equal to x minus 1. So we're going to have 2 sevenths x minus 1 to the 7 halves plus 4 fifths x minus 1 to the 5 halves plus 2/3 x minus 1 to the 3 halves plus c. Now let's look at U-substitution when we have a definite integral. There are two different methods that we can use to do this, and I want to show you both of them. So I'm going to do this example, the same example twice. Let's look at the integral from 0 to 1 of x e to the 4x squared plus 3 dx. The first method that we're going to use is, if we recall, when we do a definite integral, what we do is we first find the antiderivative of the function, and then we plug in the endpoints. So what I can do is ignore the limits of integration initially and just find what is the antiderivative of the function. So I'm going to look at the antiderivative of x e to the 4x squared plus 3 dx, and I'm going to solve this using U-substitution. So we're going to let u equal the inside function. I have an exponential, so I'm going to let u equal the inside of that exponential function. Then du dx is going to be 8x. So du is 8x dx. I don't have an 8x dx, but I do have an x dx in here. We're just going to move the 8 over. Dividing, I get 1/8 du equals x dx. So the x dx that I have can become a 1/8 du. The inside of the exponential function, 4x squared plus 3, is the u. So we have the integral of e to the u times 1/8 du. 1/8 is a constant, so it's going to hang out. When I integrate e to the u, I get e to the u. and then we substitute back. Okay, so now let's figure out how to do the definite integral. So the definite integral from 0 to 1 of x e to the 4x squared plus 3 dx. Normally when we integrate, we first integrate writing our limits of integration that need to be plugged in. Well, I know the antiderivative is 1/8 e to the 4x squared plus 3. We can ignore the plus c for a definite integral because we choose any antiderivative we like, so I'll choose the one where c is 0. So there's my limits of integration, and then I go ahead and plug them in, subtracting. So we have 1/8 e to the 4 times 1 squared plus 3 minus 1/8 e to the 4 times 0 squared plus 3. When I plug in 1 squared is 1, times 4 is 4, plus 3 is 7. So I have 1/8 e to the 7th minus 1/8 e to the 3rd. Or a fancy way of writing that would be e to the 7th minus e to the 3rd, all over 8. Let's look at another method for finding an indefinite integral. In this method, we don't ignore the limits of integration, we carry them through. So we start the same way. I need to pick a u, so we're going to let u equal 4x squared plus 3. So then du dx is 8x. So 1/8 du equals x dx, divided by 8 and multiplied by dx in the same step here. Okay. So when I write my integral, I have an e to the u. The x dx is going to become a 1/8 du. So everything looks the same so far. Here's the difference. I started off with x equals 0 and x equals 1. If I'm changing over to u's, let's change everything. So when x is equal to 0, u is 4 times 0 squared plus 3, which is 3. So that x equals 0 I can replace with a u equals 3. And when x is equal to 1, u is 4 times 1 squared plus 3, which is 4 plus 3, or 7. So my upper limit of integration where x was equal to 1, I can replace with a u equals 7. And now, if I look at this integral, I have the integral from 3 to 7 of e to the u times 1/8 du. Everything is in u's. The problem doesn't remember that it came from a problem that had x's in it, so I never need to go back to x's, because the limits of integration are u values. So when I integrate e to the u, I get e to the u. The 1/8 hangs out. And since these are u values, I can just plug in. So there's two different methods for finding a definite integral that involves u substitution.